All right, welcome back to lesson 2, example 1, part 2, and we are going to go ahead and do shear and moment diagrams for this problem, even though we don't need to. There's our answers, R1 and R2 for the existing problem. And just to go above and beyond and get used to some practice, we're going to do some shear and moment diagrams. Alright, I'm going to write R1 and R2 in their place. Okay, we're going back to the beginning here. R1, R2. So let me go back to the pen tool. And we had R1 was 4,425 pounds. And R2 was 775 pounds. And this was 1,000 pounds, I believe. Yes, 1,000 pounds. LBS. Close enough. Alright, I'm going to erase the rest of this now. If you want to go ahead and read ahead and read what shear and moment diagrams are, but you know how you originally cut the beam last chapter? Well, we could do the same thing here to find the internal forces of the beam, or this kind of gives us the forces all along the beam. So therefore this is a free body diagram. I guess essentially the free body diagram is when you have all the reactions. So this is probably more accurate of a free body diagram than before you have those. But anyways, you start off, you now have solved for your reactions. So you don't have any unknowns. This is pounds LBS. That looks a little nasty. And then instead of the equivalent reaction or the equivalent load for this uniform distributed load, we now went back to the uniform distributed load. So we have everything that we need to go ahead and do the shear and moment diagrams, and this is what we were always taught to do. This is shear. V usually means shear 99% of the time. You draw a line. Then, actually, let's do this over here. I always like to put them right on the top of each other, so we are going to keep them over here on second thought. And this usually means M of X, M at X, meaning this distance is X. The further you go to the right is X. X is to the right. So you can have, this is 14 foot. If X equals 0, then it's right here. If X equals 14, then it's right here. X equals 0, X equals 14, and anywhere along that way. Alright, so for shear and moment diagram, you always start with your reactions or whatnot. So right here, for instance, this is a good place to start. Since this is the end, we're going to start right here. And at the end, you could start right here, because at the end, the shear is always 0. But right here, the shear is going to be 775. So you could start here at 0 and go down, or you can start here and go up. But what it is you start here, and you have to know that it's 0. Actually, let's start over here. And then it's going down, and what you need to know is that distributed loads will go down at an angle. And you kind of do shear and moment diagrams by looking at the points that something's going to happen, like the important points. And I'll tell you, the important points are going to be right here, right here, right here, and then again right here. I hope you can see that. I'll change colors. I should probably change colors more. Right here is an important point. Right here is an important point. They might have a more technical name for it, but I'm calling it important. Anyways, so you want to separate it. So we're going to start right there, and we're going to say, okay, well, we have a 300 pounds per linear foot times 6 foot. So let's whip out the calculator. 300 times 6. And that's going down. This is that distributed load is going down. So we got a negative 1800. So we'll go put a point down here, and we'll call it negative 1800. And it goes from this point, which we knew the shear at the end was 0. And there. Now it goes up from the reaction 4,425. So we're going to add 4,425. We get 2625. So let's say it's about right here. 2,625. That's pounds. I'm not going to label it. We'll split over off to the side. This is in pounds. And then we're up here. We just went up. Now we're going to go down again with the distributed load, and that is what? If we had 6, this is at 6 foot, if I remember correctly. 6 foot. So that is 2 foot in between there. So we go 2 foot at 300 pounds per linear foot down. That's 600, so we have to subtract 600 from 2625, which makes it 26, or 2025. And there's 2025. Now we go down 1,000 pounds, right there, which will be, let's say about right there. Good enough. And that's at 1,025, because we went down 1,000 from the load, the point load. Now we go ahead and go distributed load again, and we're 300 times 6 is 1,800, so we want to go down 1,800. So 1,025 minus 1,800 is negative 775. So you will say, okay, it's about right there, negative 775. And you want to go right there. And then it goes up 775, so you should always begin and end, well, not always begin and end at 0. But let me think, do you always begin and end at 0? I think so. But I do believe, I have to go through my notes and really think about it, but I believe you'll always begin and end at 0 for your shear. Moments, on the other hand, is kind of the same, because if you have an induced moment, you will end at 0 because it goes back up. Like right here, we didn't really end at 0. You could say we ended at 0, but we actually kind of ended at 775, then went up to 0. In the same way you're going to do for a moment, you're going to end at some moment sometimes if it has a fixed connection on one of the sides. If it has a fixed connection over here, you would end at whatever that is in the opposite direction. Okay, so that is your shear diagram. Now we're going to move on to the moment diagram. And it's the same type of thing, where you're going to look at this area under the curve. And here is the area under the curve, and since it's down, you're going to go down. So what you want to do is look at your important points again. I'm going to kind of skim on down, because you can do that once you get past there. And you have a triangle. Everybody knows the area of a triangle is 1/2 base times height. So let's go ahead and do that. 1/2 1,800 times 6 foot. And it's negative, so you're going to have negative 5,400 foot kips. And we'll just go ahead and write foot kips over here. Everything is going to, oh, it's going to be foot pounds, sorry. This is foot pounds. And since, if you think about it, it's increasing its force, as I'll call it, and it starts at 0 and it ends at negative 5,400. But as it's going, it's getting more and more. So you're going to actually have like a parabolic, sorry, a parabolic type shape here. It's going to go slowly. It's going to be, since this load is increasing linearly, but when you're looking at the area under the curve, it's increasing parabolically. And now, since you're there, you now look over here at this section. And you want to find the area. So it's increasing, correct? So you know it'll be going up. But it's increasing slightly less. So you'll have kind of it's increasing slightly less. It'll be kind of like that. It's hard to show with this equipment that I have, but let's look at the area. So what we want to do is pretty much get the area under that curve. Not pretty much, that's exactly what we want to do. And I'm going to break it up into two boxes here. Or not two boxes, but two shapes. We have the square shape and the triangle shape. So the square shape is 2025 times, I believe, is 2 foot. Plus 1/2 times, now you want to do 2625 minus, that's distance, this right here, it's what, 600. This distance right here is 600, and this distance is 2 foot. So you want to do 1/2 times 2 foot times 600. And that's added all. So you get 4,650. And that's a positive 4,650. And that's going from 5,400, so you're going to be at 750 when you're right there. And this should line up. If you were drawing it, everything should line up. It just makes it a lot more simple so you can line up everything and see what you're doing. So you definitely always want to line up your shear and moment diagrams. So that gives you negative, this is negative 750 foot-pounds. And this is going to be increasing less and less, so it starts off increasing more. It starts off increasing more and increases less and less, but not a ton. It's not as drastic as the other one. So it's kind of like that. It doesn't need to be perfect because that would be a hard thing to do, is to get this perfect. And for this typically your max and min moments will come at one of these points. Actually, all the time they will. So just know those points and you should be fine. Now let's look at this. It is actually, at this point you don't even need to do this. What you do is, which this is a nasty problem, and there's probably a reason they didn't want to do what they're doing. They typically will make it easy to figure out. This one is not so much, because you have to figure out. We know the slope of the line, correct? We know this slope. So we need to find this intercept right here, which, give me a second, I will figure that out. And because I'm running really low on time, I just fast forward it. It was actually extremely easy. This is, if you remember your calculus, that up here is 300. So this, since it's negative 300, since it's distributed load, this slope is 300. So you'd make quick equations, say 1025 minus 300x equals 0. Remember that x is from this point. So it's 3.42 from there, and 2.586 minus 3.42 to this. And we go ahead and we look at this important point, and we say 1025 times 0.5 times 0.32 equals 1000. This is 1002.75. And then we should be going down. It inserts a 0, and it goes to there. It gets greater. It's a greater negative. So that's what the slope should look like. And when you do the math for this triangle right here is 0.5 times 2.58 times 775. You get around 1,000, and this was around 1,000. That was around, it was 1,000.2, and I got 99.75. So you'd meet actually around 3 foot kips. But when you get really close to 0, you just know, okay, well, I rounded different things, so you actually say, oh, I got back to 0. So that's good. What you take out of this is, look, I got a maximum positive moment and a maximum negative moment. And if you're designing a beam or a slab or whatever you have, you need to, your maximum negative moment is going to be your top steel. If this is a concrete beam, and this is going to be your negative steel for positive moment. All right. Hope that helped. Anyways, it should be easier going forward.